Hello everybody. Today we have to start our chapter number 5, that is compensator design. Okay, so let's start this unit. So before starting that actual compensator design and all of the controllers, let's talk about the block diagram of a process control system. So generally we have seen that there are different types of control systems like open loop, closed loop. Okay, but ultimately if we see, the goal of our control system is to get desired output. Okay, so let us talk that control system in terms of a process. So here if you see, this is our process, or we can say the task that we have to do. Then the output is measured with feedback element. Okay, so measurement is done here, and if you see, this is the output and a measurement is taken over here, and if you see, this is a B as a feedback. Okay, and here there is a summing point. If the feedback is negative, then the error will be difference in between R and B. If the feedback is positive, then error will be R plus B, like this. Okay, so if you see the sign of this one, as per this sign, this error equation will change. Okay, I think you know this. Based upon this feedback and reference input that we have applied, the error is applied to the controller. Okay, and the most important thing is done by this controller, because ultimately it is referring input, it is referring the feedback, taking the error as an input, and as per this error signal, it is giving the output to the control element. Okay, so whatever the control element will do, any act, that depends upon the output given by the controller. That is very important. Okay, so control element is just an interface in between controller and processor. Whatever the signal given to the control element by the controller, that is given to the process to get a desired output. That is very important to understand. Okay, so that's why the most important concern about the design is this controller. Okay, but sometimes due to some system characteristics, the error that we are getting will be having some errors. Okay, so that's why as per this error, controller will act. So that's why, to reduce that to some extent, not 100%, to some extent, we can say we have to design our controller. Okay, so means what, we have to just compensate the signal here or the output of this controller, so that we can get actual output. So that is nothing but your compensator. Okay, so I think you got the idea about the process control system. The most important is controller, and we have to talk about this only in this unit, how to apply the output of a controller to the control unit by different ways. Okay, so if you see the classification of this control action that we have discussed, it can be discontinuous or it can be continuous. Okay, so in discontinuous, it may be on-off controller. Okay, like a 2-position controller, multi-position controller, and floating mode controller. Okay, so basically this is very simple. Discontinuous means what, for some period it will be off and for some period it will be off. Okay, so on and off period will be there, and I think this is very simple. Okay, just if you say, if you have seen that PWM waveform like that. Okay, so this will be like this. Okay, so that's why we are not going to talk about this on-off controller, because these are very simple. We are interested in continuous control actions, because this control actions which is continuous, which may give you it may give you desired output. Okay, so the continuous action only is very important than the discontinuous. Okay, so if you see this continuous output, it can be proportional, it can be integral, or it can be derivative. Okay, so again, one point I want to mention over here is that if you know actual use of integration and derivative in real life, then you will easily understand this unit. Okay, so there will not be having any trouble inside that. Okay, so you will understand easily. So that is my main concern about this unit, because you must know how the integration is useful in real life and derivative is useful in real life, or what is the actual meaning of that. In mathematics you may have studied this integration and derivative, you are just using the formulas and you are solving that integration and derivative and you are getting marks, but that is not important. You must know why integration is required, why derivation is required, what is the difference between integration of something and derivative of something, okay, and why they are opposite to each other in some ways, okay. So this you must understand. So again, if you see the continuous controllers that we have discussed, that is proportional, integral and derivative, but again they can be used as combination of anything, okay. So like a pi or pd or pid, like this, okay. So we have to discuss these, okay, which are very important. And I think if you understand this proportional, integrated and derivative, then you will understand easily pi, pd and pid, okay. So let's discuss about this control actions. So let us start with the proportional control action, but before that, some related terms you must understand. Continuous controller that responds to continuous input variable are called as continuous controller. Right now we have discussed about this. Discrete controller, like on-off controller, that responds to discrete signal. The process equation describes the mathematical relation among the input and output of a variables. I think these are basic terms and we have studied this. Now let us see just a difference in between proportional, integral and derivative, how they react, okay. So suppose let us select one test signal like a step input, okay, and suppose a system is proportional, one system is integral and another is derivative, suppose. And if I apply the step input to proportional, integrative and derivative circuit separately, so what will be the output of this, that we have to see. Whenever we are applying the step input to the proportional system, then you will get some level of amplification like this. Same signal will be there, but with amplified version, okay. Now note that this is the output and this is with respect to time, okay. Sorry, this is the output and this is with respect to time, and this is the input which is again with respect to time, okay. So this is the input and this is the output. Whenever the system is integral, then when we apply this input like this step input, then we will get a continuous increasing slope or graph like this, okay. So I think you have studied or you may study in future, whenever the square wave is applied to the integrator circuit, electronic circuit, then it will convert that square wave into triangular wave. So that is the reason behind this, because it will give you a continuous slope like this. So please understand this. These are the basic signal and which are very important to understand the next points as well, okay. So here as I discussed earlier, for the step input it is giving you a increase in a slope like this, okay. So if it is a derivative, it is continuous signal and I think it is constant signal. You may see this, you are getting a derivative like this, and I think you have studied the derivative of constant. So the basic idea behind this proportional, integral and derivative is given over in this picture, okay, and it will be very useful to understand the next concepts, okay. One important thing that you have to do is that just take any sine wave and see how the integration of that sine wave comes in a graphical way. Take any triangular wave and take the integration of that actual wave that you will get. Same concept should be applied to the derivative circuit as well. Apply the sine wave, apply, we can say, triangular wave, square wave, and see the output how you are getting. There may be online simulators and you will get the output like this, or in graph also on Google you will get good information about this. Then you can understand how the derivative is, how we are getting a derivative if you apply particular type of or shape of signal, how we are getting integration of that signal and all, okay. So this is very important and interesting that you have to study. Now let us start with proportional action. See, this unit is very easy to understand and just you know the basics very well, like integration, derivative and proportional. I think proportional is again very simple. Let us talk about this proportional control action. In the case of a proportional controller, the actuation signal is proportional to the system deviation. Okay. If you see the system deviation here, the actuation signal is proportional to the system deviation. Okay, so this actuation signal depends upon the system deviation. The meaning of this line is that if the system deviation is large, the value of the manipulated variable is large. Similarly, if the system deviation is small, the value of the manipulated variable is small. Okay, what do you mean by system deviation? That system deviation is given to you by that error signal that you have to understand, because we have studied that basic diagram that you have to keep in mind every time whenever you are studying the concepts like integral, derivative and all other things. Okay, so the time response of the P controller in the ideal state is exactly the same as the input variable. So let us see here. So if you see, this is the control, this is the feedback signal or measured state or measured signal, this is the desired signal or reference input that you have applied, this is the summing point, and the error signal is given over here. So now this error signal will be multiplied to this proportional constant and you are getting a control signal. So in other way I can say that this control signal is proportional to this error signal. Okay, and this error signal depends upon the deviation of the system. So that's why it is written over here. In case of a proportional controller, the actual actuation signal is proportional to the system deviation. Okay, I think you understood this. Here it is shown clearly. Suppose the system deviation is like x0, okay, and or we can say the system deviation is given over here in left side, and the manipulated variable or controller's output we can say is given over here. Okay, so here this much is, we can say x0 is nothing but your error signal or deviation, and that is, we can say, amplified with the help of the proportional control action. So this y0 is directly proportional to x0. So that's why whatever the xd that you are going to apply here, system deviation, that will be multiplied to the controller's gain, and that is getting over here, and we can say here in this case that is a y. Okay, and if you see the more information about this proportional controller, in a proportional control mode, a smooth linear relationship exists between the controller output and the error that we have discussed. And the range, if you see the range of the error to cover the 0% to 100% controller output is called as a proportional band. So whatever the range that is 0% to 100%, that is a proportional band. Okay, because the 1-to-1 corresponds exists only for error in this range. So why this 1-to-1 correspondence? Because it is directly proportional to the, we can say, error. Okay, so this is all about the proportional band. If you see the mathematical equation, the output can be expressed as P is equal to Kp into AP plus P out. Okay, so here P out is very important to understand, control output with no error. Okay, so there will be some output, actual output, without applying any error, because it will not whole and soul work on that error signal. It will be having some, we can say, offset or something, we can say set output. So it will be like P out, so control output with no error, and Kp is the proportional gain between error and controller output. So collectively, shortly if you want to express, it will be Kp into Ep, but in detail if you want to express this, it will be Kp into Ep plus P out, which is nothing but control output with no error. Okay, so in some books it may be given like this only, P is equal to Kp into Ep. Okay, in some books it is given in detail like this, P is equal to Kp into Ep plus P out. Okay, so in a proportional control mode, the proportional band is dependent on the gain and can be expressed as, so proportional band can be given by 100 divided by Kp. Kp is nothing but proportional constant of a controller. Okay, Now in terms of the we can say control system fashion, if you want to represent it, the diagram will look like this. This will be reference input RT. It is given in a time domain, okay, that you have to understand. RT is a reference input, BT is a feedback signal, ET is error in between reference and feedback signal. This is the proportional controller having gain of a KP, okay, and output of a KP is CPT. It is again time domain, and it is multiplication of KP into ET that we have discussed earlier, and this CT will be the output of a plant whenever the input of KP into ET is applied. Okay, so this is all about the time domain we can say representation. So if you see the output of a controller that is given by KPT is equal to ET into KP, okay, sorry, CPT is equal to KP into ET, that we have discussed earlier. Now if you take a transfer function or in S domain, the KP can be given like KPS divided by ES, because if you see here, this ET will go to the denominator side here, and it will, if you take a time, if you convert this time domain into S domain, it will be CPS divided by ES is equal to KP. Okay, so this is all about the proportional controller. Now another important thing is that what is the relation between that gain and the proportional band. Okay, if you see the proportional band of a proportional controller depends on the inverse of a gain. So there is inverse relation. Okay, so from this diagram we can conclude that suppose this is the gain G1. Okay, so if you see this controller band which is narrow, so the gain of this controller, suppose proportional controller, is G1, and if you see this wide band proportional controller which is having slope like this, that is having some gain like a G2. Suppose G1 is greater than G2 or G2 is less than G1, then if you see the gain which is having higher value will be having narrow band, and the gain which is having lower value will be wide band. Okay, so here you will get a smooth increase, and here you will get a fast increase. Okay, so that is again important. So this is again control output versus error, percent error. Okay, now whatever the range of this gain or we can say the range or band of this error, if you want to decrease or increase the band of this error, then you have to adjust the gain. Okay, so that's why the proportional band of a proportional control depends on the inverse of the gain. Okay, so if you increase the gain, this band will be decreased. Okay, so again if you take a gain as a G3 which will be greater than G1 and G2, then this narrow band will be again shorter. Okay, so I think you got the idea about this. This is center, this is positive, and this is the negative error we can say. Okay, so if you see the characteristics of a proportional control mode, okay, there are some characteristics, there are some advantages and disadvantages that we have to discuss. If error is 0, the output is a constant equal to P out. Okay, that we have seen. If there is an error, for every 1% of error, a correction of a KP percent is added to the or subtracted from P out depending the sign of the error. Okay, so in this equation, in the equation of proportional controller, we have seen this. Now what are the advantages of a proportional controller? The most important advantage is it is very simple. Second is these controllers has high loop gain. Okay, the loop gain is very high because it's directly proportional to the error, that's why it is having a high gain. It has steady state tracking accuracy. Okay, it stabilizes the gain and make the system more stable. Okay, if you adjust the gain of the controller as per your applications or specification, you will be somewhat successful to adjust the gain or stabilize the gain, we can say. Okay, so this is all about the proportional controller. What are the disadvantages of a proportional controller? Yeah, there are disadvantages. Okay, so that's why they are not mostly used. The first is it cannot accommodate load change without sustained deviation. Okay, so this is again the disadvantage. It cannot accommodate the load change without sustained deviation. It produces the constant steady state error. If there is error, it produces that error constantly. For very large gain, it leads to instability of the system. Okay, if you take the higher gain, then there will be a fluctuation. There may be a fluctuation, and due to that, there may be an instability. It has a sluggish, that is a slow response for wide proportional band. Okay, so we have seen that here. If you see the wide band, then it will increase slowly. So suppose again if you increase this band's width, again it will again become slowly. So that is given over here, that is it has a sluggish or slow response for wide proportional band. Okay, next is it makes the system less sensitive to parameter variation. Okay, so there are some parameters, and that parameter variation, this is insensitive. It is sensitive to error only, maximum. Okay, so these are the disadvantages. Okay, so let's see the next point. Next is integral control action. Okay, I think we have discussed much about the proportional controller. Okay, so in detail we have seen the what do you mean by proportional controller. Now let us see basic idea behind the integral and derivative, because we have to see PID controllers again. Okay, so that's why there is need to understand this basic idea behind the integral and derivative controller as well. Okay, so the integral controller adds the system deviation over time. Okay, it integrates the system deviation. So whatever the system deviation is there, it is giving you the integration of that. Okay, we will see in a block diagram or in a picture representation as well. Don't worry about that. Okay, so as a result, the rate of a change, okay, not the value, that is important. We are talking about the rate of a change, not an exact value. So the rate of a change of the manipulated variable is, we can say, proportional to the deviation. Okay, proportional means what? That it is taking a integration of that system deviation. Okay, so system deviation के हिसाब से वो क्या करेगा कि इंटीग्रल आपको देगा. So that is very important. This is demonstrated by the step response of a I controller. Means what? If the system deviation suddenly increases, the manipulated variable increases continuously. Okay, just recall in proportional control, if there is sudden deviation, then it will be a sudden spike, sudden increase in the gain at the output. But in case of integral, if the system deviation suddenly increases, the manipulated variable increases continuously. That is very important. Okay, and that is important characteristics of an integral action. So let us discuss about this. Now suppose the system deviation is like this, the step input, this is the XD, then manipulated variable or controller's output will be continuous increasing, we can say slope or a graph. Just recall the proportional, if you apply the input like this, it will suddenly increase from this at the output, and that may be harmful to the system. Okay, so if you see the integral action, it is continuously increasing. Okay, so this is very important to understand. Okay, now let us discuss more about this. The greater the system deviation, the steeper the increase in the manipulated variable. Even though there is a greater system deviation, the step by step slowly it will increase. For this reason, the integral controller is not suitable for totally compensating remaining system deviation. Okay, so due to this characteristics is not suitable for totally compensating the all system deviations, okay, or remaining system deviations. If the system deviation is large, then manipulated variable changes quickly. Okay, again, suppose if it is very large, then there are chances that a manipulated variable changes quickly. Okay, based upon again the input deviation that you are going to apply. Okay, as a result, the system deviation becomes smaller and the manipulated variable changes more slowly until the equilibrium is reached. Okay, so a pure integral controller is unsuitable for most of controlled systems, as it either causes oscillation of the closed loop or it responds too slowly to the system deviation in a system with a long time response. Okay, so again the slow response is there. In practice, there are hardly any pure integral controller. Okay, so practically you may see different proportional controllers, on-off controllers, but practically integral controllers are not there in use. Okay, so let us discuss in terms of mathematical expression. An integral controller mode, the rate of change of control output is proportional to the error. Okay, and integral proportional we can say. So the output can be expressed as Pt is equal to Ki integration of Ep dt plus P out. Okay, or we can say P0. If error is 0, the output is constant equal to P0 or P out. Okay, so here the characteristic, if you see the important characteristic similar to proportional, if error is 0, the output is constant equal to P out or P0. Okay, if there is an error, for every 1% of error, a correction of Ki percent is added to the or subtracted from P out depending on the sign of the error. Again, it is similar to the proportional action we can say, but it is integration. See, this is the integration. So if you see the integral controller, a purely integrating controller is slow. Okay, error takes long time to build up. Okay, that is again one important point. The error takes long time to build up. Action can become too strong, like overshooting if the gain is very high or system deviation is very high. Integral controller is unaware of current position. Okay, so they are not aware of the current position. Generally used combined with or used with P control, and that can be called as a PI control, that we have to study afterwards. Okay, so this is all about the integral controller. So generally they are not we can say uniquely used because they are used with proportional controller to get advantage of proportional and integral controller. Okay, then if you see the advantages of a integral controller, it reduces steady state error, that is effect of offset. Then it provides high control output at a particular time after the error generated is for high value of Ki. It responds to the continuous existence of a deviation. Okay, so this is important. Again, it responds to continuous existence of a deviation. Continuous increases there. And this is the again important thing that you have to keep in mind, that it reduces steady state error, that is effect of offset. So this is the important, I think very important characteristics of a integral controller. In case of proportional, it is not possible to reduce steady state error, but in case of a integral controller, it reduces the steady state error. Okay, so this is very important characteristics of a integral controller. I think for this lecture this much is sufficient, and in next lecture we may start with derivative control action. Okay, so before that I think one point is remaining that we have to complete, that is disadvantages of an integral controller. We have discussed the advantages, now we have to discuss the disadvantages. So it is never used alone, that I have discussed earlier. It makes the system unstable for oscillatory response. If the system response is oscillatory, then it will be very tedious for us, so that's why it is not used alone. It introduces hunting in the system response about its steady state condition. Okay, so in next lecture we will start with derivative control action, and one important thing is that we have studied the proportional in detail. We have seen some important points related to integral. So during study of that proportional and integral part, just take positive points of a proportional and integral controller in your mind, because they are combinedly used for their advantages. Like if you take a proportional and integral, then it is used by taking advantage of proportional and integral controller like this. Okay, so for today's lecture, for this lecture, this much is sufficient. We'll meet in a next lecture. Thank you.